Hi, everyone. Today we're going to finish up just talking about free text and natural language processing, and we're actually just going to finish that. I'll discuss what's going to happen with geographic information systems in a second, but I think it's actually a reasonable solution. Okay, so some quick announcements. Homework 3 is out tonight, as you all probably know. We're going to send the feedback on your tutorial topics tomorrow. We're just working to get the homework out before then, so we'll send feedback tomorrow. For the most part, we've glanced over it. Most people are fine. We're pretty general in what we allow for topics, so I think most people should be fine. But those people that do have maybe too narrow a topic, we will let you know. Third, there was a little bit of a glitch in the Piazza poll. I don't know if it's a glitch actually technically or not, but apparently Piazza, when you have a poll, doesn't actually allow you to say what people voted, just the fact that they did vote. So we had a bunch of people, they all voted to switch, and unfortunately the listing of the people and the current courses did not match with the things they voted for. So if you are aiming to switch, you should have gotten an email requesting you fill out a different form. If you did not, let me know. But you should have gotten an email asking you to fill out a different form just so that we can finish that. And we will do that all tomorrow. So sorry about the delay on that. I did not realize Piazza would not actually give you the option to see what people were voting, just that they were voting. I don't know how that's very useful. The next thing is that actually, and this actually relates to what we're going to do with the Geographic Information Systems lecture. So originally this lecture today was going to be about geographic information systems and handling spatial data in general. In general, I think that's a very important topic for data science, but it's one that's a little bit less important than these other topics we've covered so far. So we decided to kind of just squeeze that away out of the course. We'll probably do the same with some other later ones, more advanced machine learning methods. We'll probably squeeze those as well. The thing we're going to do and simultaneously, we're kind of hoping to sort of accomplish two things at once with this. Simultaneously, a lot of people have been asking us for a little bit more guidance in terms of what we want in a tutorial, because we've said we linked to this other book on some Monte Carlo methods for probabilistic systems, but that's a whole book, right? And it's sort of unclear if that really tells you what to do in a tutorial. So we're going to put up a tutorial probably over the weekend or later this week on geographic information systems. And so the content that would be in that lecture will instead be in this tutorial, and it will also serve as a template for the kind of thing we're looking for in a tutorial that you guys would do. So this will be an example of the kind of thing that we want. That being said, it will not be restrictive, and that you don't have to do something just like that. We're trying to cast a pretty wide net here, but it will at least hopefully give a little bit more insight into the kind of things we're looking for, the kind of balance between prose and code and this kind of stuff. So and then everyone should also go through that, both to learn about the tutorial and also to learn about the topic of geographic information systems, which we're not going to cover. Anyone that has any spatial component, sort of any component of analyzing spatial data, though, in their project, perhaps, will definitely want to sort of look at that a lot, and hopefully you can still get a good sense of what we were going to cover, just in tutorial form. Lastly, we're actually going to also switch website hosts tomorrow. So this website it hopefully won't go down because the other server is up and running. It's just that the DNS is linking to our current one right now. We're going to swap that over tomorrow. Hopefully it'll be seamless and no one will even know. But just FYI, it might go down for a little while tomorrow. So if you really want the next homework, download it either late tonight or early tomorrow morning. I don't know what time exactly tomorrow, but it should be down for very little time. If it's down for a long time, we'll post other links or whatever to the homework. All right, so today we're going to keep talking about free text in data science. Before I get started, though, are there any questions from last time? Yeah. So the question was, is there a hard deadline on switching? The answer is no. As long as you are, say, in 388 and doing the 688 problems, you can switch at any point. If you're in 688 and haven't been doing the assignments, you'll be able to switch down. You might as well do that right away. Otherwise, you might, probably aren't going to be doing the best in 688 if you're missing one question per homework for every homework. But no, there's no time. If you know, we'd appreciate you, I guess not filling out that form because now it's useless, that form, but At this point, probably just write a note on Piazza saying you like to switch. If you do want to switch, and we'll switch you over. Yeah.
For the PageRank algorithm from last time,
Mm-hmm.
if you had a different notion of importance of nodes rather than just like where they're placed,
Yep.
do you like build a heuristic, and then where would you put that heuristic in the algorithm?
So the question was, if you had a different notion of importance, could you somehow integrate that notion into the algorithm instead of the normal PageRank one? That's kind of a hard question to answer because depending on your notion of importance, it could be one that could or could not be captured by this sort of process of a random walk on the graph. I mean, the PageRank, very, very fundamental to the PageRank algorithm is that what it's doing is it's simulating a random walk on the graph, and then it's sort of looking at where you may end up when you follow this walk. If you have a completely different notion of importance, it's hard to see exactly how you would, encode a different notion that you want to encode. But there are other tweaks you can make to PageRank to get it to do different things. In fact, actually, someone mentioned as a possible tutorial, I think, talking about the kind of attacks people did on PageRank, and then how that's addressed. For example, one thing you can do to highlight importance in PageRank is you can create a dense cluster of sort of very highly connected websites. And if these are all very highly connected, then you can actually kind of inflate their PageRank, right? That was a technique people used for a long time, these sort of big pages that just linked to every other page that the spammers wanted to bump up. It has since gotten a lot more difficult to do that. So the idea was then there was some notion where you think that those are not important, those pages, and so they added tools where you have to sort of start at some legitimate page and you don't branch too far out from those things. But there have been these other sort of notions of importance and changes to PageRank, but I think in general it's hard to sort of talk about arbitrary other measures because oftentimes the measure itself will imply an algorithm. Well, I should also mention too, I just sent out a note about this on Piazza. Maybe you all got it. I think I checked the box to email everyone. But we're also going to open up attendance now. I think we've filtered down enough where people have reached an equilibrium point of watching videos instead of coming to class, which again is fine. But we're going to open up attendance to the 688B section. So maybe, though they may have all been completely used to watching videos now and very happy with that. People have told me they watch me on 2x time, which I have no idea how that's possible because I talk too fast on 1x speed, and so that's amazing. But if you can actually do that, then maybe it's more efficient that way. But we are opening up attendance to the B section, and hopefully those that want to attend that couldn't have been able to before are now welcome to attend. Okay, so let's jump back into free text. So last time, I'll just summarize because hopefully you actually have plenty of time now. We'll see if I actually still get behind yet again on this lecture, but hopefully not. We talked sort of briefly about what we mean by free text and natural language processing in heavy quotes for data science, because I think what we're doing is really pretty simple in a lot of respects. All we want to do is extract some information from text. Our goal here is not to understand the true nature of the language, of what's being said, and the true sort of syntactic meaning of the text. I actually forgot to add one definition to my list of terminology here. So I mentioned before that we're going to talk about kind of two things. We're going to talk about documents, which in general can be actual documents. They could be a web page or something like that. But they can also just be an entry in a relational table, right? So a document is just a collection of text, or a collection of words. Words are terms refer to the individual tokens in that document. And finally, I didn't have this one before, but I had forgotten to add it. But a corpus refers to a collection of documents. And so the corpus is kind of the universe of all documents you have. So in our example here of these three documents, the collection of these two documents would be our corpus. And so really this X matrix here is representing our entire corpus, not just an individual document. All right, so I'm going to use that term later, and I wanted to make sure that it was defined before I did. Okay, so when we stopped last time, we talked about this term frequency matrix, and essentially it's exactly what you might expect. It is the unordered version of what words are included in a document. So all we care about is the words that are there or not and how many times they're there, not the order they are in. And there are actually, as I mentioned last time also, a few different possibilities. Even something this simple, there's actually a few different possibilities for what we can include in a term frequency count. It could be binary. Oftentimes, it's just the actual number of times a word occurs in a document. That's kind of the default term frequency, as you might imagine. But there are some other options. So there's also a 0-1 count of term frequency. Does it appear or not? There are also things like log scaling. So this function here, the log of 1 plus the term frequency, if term frequency is 0, this term will be log of 1, which is also 0. As you get more counts, though, rather than that entry growing linearly in the number of times a word occurs, it just grows logarithmically. So it sort of tapers off after a while and grows at a much slower rate. And this is kind of nice if you don't want certain words that appear a lot to kind of dominate the counts there. That can sometimes put too much weight on very common words in the document. So you might want to smooth that a little bit by having a log scaling of your terms. We might also want to scale globally by, say, the maximum number of times any word occurs in this document. So maybe rather than having just the term frequency be a number that's a count, an integer, we'd have it be actually a number between 0 and 1 because we regularize each document or normalize each document's counts by the number, by the, say, the maximum count in that document. You could also, of course, normalize by the total number of words in the document and get a probability distribution along each row in the matrix. But this is really just showing that there are multiple possibilities here, and there's no lack of different scalings and different kind of heuristics people use to try to weight these things in a better way that maybe performs a little bit better. Where, by the way, what we mean by perform better will hopefully become clear a little bit later. Okay, so that's the sort of the simplest thing you can imagine, right? It's just a matrix that describes a corpus, a collection of documents, by just the number of times each word occurs in those documents. It turns out, though, that this by itself sometimes naively would give put a little bit too much emphasis on words that are kind of very common across lots of documents, right? So if you look at this matrix here, the words that get highest count, the words that are, have the highest counts in these documents, and this is true for a lot of the English text, are the words that are just sort of very common across all English language, right? So the and of both, I mean, this is a simple example here, so it's not too interesting, but the and of both occur twice, but you wouldn't really say that these are very important for that first document, right? These are just sort of words that occur all the time. So we really doesn't matter. We aren't helped to say determine if if it's a movie review, we probably aren't helped very much by saying how many times does the word the or of appear in some review, right? So in terms of actually using the information in these bag of words models, we don't really care about things that happen a lot, right? That's sort of some sense that if they occur in every document, say, it probably isn't that useful of a term to think about. Now, we can mitigate this problem a little bit by using what's called stop word lists. So stop words are just lists of words that are kind of considered to be common words among English, and so they are typically thrown out from any set of documents. So you take a corpus, you take each document, but you throw out the stop words and you don't consider them, you don't actually include them in your term frequency matrix. But this is kind of a hard-coded process, and we'll actually see how to do that later. This is, you can do it in one line in Python. It's actually quite easy. But this is kind of a hard-coded process, right? Because it doesn't specialize to your actual corpus at all. If you have a collection of documents, it will not actually say that, if all your documents are about the election, right? I think actually the tweets assignment you have talks a lot about the election, or at least relates to it. But if you have a set of documents about the upcoming election, then the word election probably appears in a lot of them. But that word is probably not on a stop word list of English, right? Because that word doesn't appear that often in normal English text, but in your corpus it appears very often. So we want some specialized way of actually also degrading the importance of words that occur very frequently in your corpus, so that they won't be kind of as influential as words that are specific to that document. Because there's some notion where the words that are specific to that document, at least if they occur more than just once. Maybe if it occurs once, you maybe can't do much with it either. But if the words occur multiple times, but only in a few documents, those words somehow seem to be very important to us, right? And this notion, a notion called inverse document frequency, kind of captures this idea. So inverse document frequency, and again, the problem here is that term frequencies tend to be overloaded with very common words. Those could be stop words, but they could be any word. So inverse document frequency tries to get around this by weighting words inversely to how often they occur in the entire corpus. Right? So it's a very simple formula here. As with term frequency, there are a lot of different possible modifications of it. Here, it's very standard to use a log. So I'm going to include the log in my definition, though you could get rid of the log if you really wanted to. But the idea is very simple. We take the number of documents with word J in it. So that's the number of times, number of documents that contain some term. So if I'll go through an example in a second. And we take this, I mean, you can think of this as this term divided by the number of documents would be the proportion of documents that contain that term. That would be the document frequency. The inverse document frequency is then just the inverse of that. So it's the number of documents over the number of documents with word J. So there'll always be a number bigger than 1, right? Because there's always more documents than terms that can include a specific term. And then we take the log of that. And the reason we take the log is, again, we actually, here we almost always want to discount this a little bit. We don't want to treat this as quite as important as the term frequency. Otherwise, it would sort of have very, very big values here that would give all the importance to a term based upon just how often it occurs, not how often it occurs in that document. And so therefore, we almost always take the log here. But again, there are other weightings you can use as well. Now, it's important to note that term frequency, and I'm kind of trying to hint at this by using the same indices here. Term frequency is defined for both documents and words, right? Because it's a count of how many times this word occurs in this document. Inverse document frequency is a quantity that's defined only for a term, though, right? Only for a word, because you're then averaging over the entire, all the documents, the entire corpus, and so there's no I subscript on the inverse document frequency, just the J subscript. Here again, before we're using we're using the I subscript to index over documents and the J index to index over words. So I'm just using a J subscript on IDF to kind of emphasize that. Any questions on this? Hopefully pretty straightforward. We'll go through an example in a second, but again, I think it's largely intuitive. So let's take an example. Let's look at the inverse document frequency of the word of. So of occurs, remember here we don't actually count the number of times it occurs. We just say how many documents does that word occur in, period. So the word of occurs in 3 documents, because it occurs in every document at least once. And there are 3 documents, so it's the log of 3 over 3, so that's 0. And you see what happens here is exactly kind of what you might expect. If a word occurs in every document, this inverse document, the thing in the inside of the log, will always be equal to 1, because it occurs in every document. And so the log of that will be 0. So any word that occurs in every document will be completely discounted in TF-IDF. And that makes sense to a certain extent. I mean, maybe you might say, okay, well, it also discounts how many times it occurs. But the reality is if a word occurs in every single one of your documents, it probably is not that useful for distinguishing any characteristic of your documents. And so you might as well just kind of throw it out. That's the idea anyway. Though again, you could add, a 1 plus the thing to always have some term in there so that, the minimum would not be actually 0. It would be something else. In fact, actually, the library that we're going to talk about that does this actually doesn't quite throw out words if they have 0. Even if they occur in every document, it won't quite throw them out. It does something a little different, which we'll mention at the very end of the class. But we can just repeat this for other words. So the word is occurs in 2 documents. And so the IDF is the log of 3/2, which is 0.405 about. And similarly, the IDF of goal is log of 3/1, because it occurs in 1 document and about 1.1. And importantly, of course, this is actually this covers all the cases, right? Because there are only 3 documents, so it doesn't matter which order of document they occur. It doesn't matter which documents it occurs in. It's just based upon how many documents the term occurs in. And so every IDF term for actually every one of those terms will be either one of these 3 quantities, right? Depending on whether it happens 0, well. But you don't worry about 0, because if it doesn't occur in any document, we don't even put it in the matrix at all. But based upon whether it occurs 1, 2, or 3 times, it has one of these 3 scores. Any questions? All right, and now we can finally define TF-IDF, which is exactly what you might expect it to be. It stands for term frequency inverse document frequency, which all it is just the product of these 2 things. This happens to have sort of experimentally proven to be a pretty good way to quantify the importance of terms in a document, is the product of the term frequency in that document and the inverse document frequency of that word. Again, where the inverse document frequency has this log term built in, so it has in some sense a little bit less weight, maybe you can think of it, than the pure term frequency. And the idea of a TF-IDF matrix is you just replace the actual raw counts in the X matrix with their TF-IDF score. And that's all it is. Seems really simple. There's actually very little theory to back up why this is a good idea. People have tried to develop something to have to do with things like Zipf's law. If you've heard of that ever, I won't go into that. But the reality is there isn't too much justification for this other than it seems to work well. And when I say work well, what I mean is that if you want to do things like compute similarity between documents, say, which I'll talk about how you do in a second, or if you want to build a machine learning algorithm that uses these numbers as features, which you actually will do in your next assignment, that uses these numbers as features, I think you're just going to use the raw counts in the 388 assignment, but still, maybe you can do better by doing this. The point is, if you have one of these scenarios, it often works better in practice to just replace the term counts with TF-IDF scores instead. It's just sort of an empirical fact. This seems to be a good weighting, a good way of gauging the relative importance of frequency and how often a word occurs that works well for these things in practice. And that really is actually all that I'll kind of say about it. Just know that it actually, if you're going to use bag of words, it is definitely worth trying to use TF-IDF scores instead of just the raw frequencies. So the last thing I'll say about the bag of words approach is this final notion we have now. We're going to use these definitions to define something called cosine similarity, which is actually a fancy name for something really easy. It's just an inner product of 2 vectors describing a document where you first normalize each vector. Okay? And normalize in this case by the 2 norm of the vector. So the cosine similarity is just the inner product of 2 vectors describing the 2 documents. So if we have the first row here would be a vector. It could be either TF-IDF scores, or it could actually also just be term frequencies. But the first vector here describes the first document. Second vector describes the second document. So the inner product of these 2 vectors divided by the norm of each vector times each other is just the cosine similarity score. And by the way, the reason why I say it's the same as just thinking about normalizing the vectors first is you can think of this actually as you take x, you normalize it. You normalize it by dividing by its L2 norm. That's just the Euclidean, that's just the square root of the sum of the squared entries. That makes x also have norm 1. Similarly, you do the same thing with y. And then you just take the inner product of these two vectors. That's the same as taking the inner product and then dividing by their two norms. So it's just really a normalized inner product between these two vectors. And it goes by the name cosine similarity. It does that because actually you can think of this quantity as the cosine of the angle between the two vectors. This is what it technically is, but that was never that intuitive to me anyway, because these are high-dimensional angles that I don't really even know what an angle means, and it's not a useful concept to me. What does matter is that this is going to be a score. Oh, I said oops, between -1 and 1. No, sorry, between 0 and 1, right. If x and y can be negative, and then in general this quantity could be between -1 and 1, but because the counts are all positive, it's always going to be between 0 and 1. If the two documents have no overlapping words, then every element, actually maybe I'll just write this up because we haven't done much linear algebra yet, so it's very, very simple here though. Remember that x transpose y is equal to the sum from I equals 1 to n. If there are n, in this case, n total words in the entire corpus, and total unique words in the entire corpus of xi, yi. So if every word, if document 1 and document 2 have no words in common, this score will be 0, right? Well, because this inner product will be 0, and then you're sort of, that's it. Everything's going to be 0. If x and y are the same, then this quantity will be equal to 1, which you can tell just because you then have x transpose x. But when you normalize, you then divide by the 2 norm of x times the 2 norm of x. And that gives the 2 norm of x squared. And the 2 norm of x squared is just actually equal to x transpose x over. This is just actually the exact definition of this, which equals 1. So this quantity is going to be between 0 and 1, depending if the documents are completely disjoint in all their words, it'll be 0. If they're exactly the same, it will be 1. And then, of course, in the intermediate case, you have other values. So we can look at what these things look like. So this in this case, I'm computing the TF, not just the counts, but the TF-IDF scores of these 3 documents here. And then I'm forming a matrix which is all the cosine similarities. So the way to read this is the cosine similarity between document 1 and document 2 is 0.068. Between document 1 and document 3 is 0.078. And between documents 2 and 3 is 0.103. This would probably be higher if you use the raw counts themselves, but it's relatively low because we're using the inverse document frequency, which again kind of puts more weight on things that are unique to the different documents. And so in this case, actually, kind of makes all their similarities a little bit smaller. But as you can imagine, I mean, this kind of captures hopefully, I guess, what you might think. I mean, it seems like sentences or documents 2 and 3 are a little bit more similar. They both have this phrase bag of words, even though 1 and 3 have the text processing in common. Then that's sort of a small portion of the first sentence, so it doesn't play as heavy a role. And similarly, sentence words, or rather documents 1 and 2 seem kind of the most distinct because they have some overlap, certainly, but they don't really have that much in common. Just words like is and such like that. So that's, and you can go and compute this all, make sure that they're right, but hopefully it's pretty straightforward, the computation we're doing here. Okay, so let's move on now to something a little bit more complex because admittedly, the bag of words approach is very limited. And we're going to talk now about some very, very basic language models. In particular, we're going to talk about what are called n-gram models. So, bag of words is sometimes actually, considering how much information we are throwing away, it's actually surprisingly effective a lot of the time. Because we're throwing away just everything that actually makes language language, right? Language is not a bag of words. You can't jumble up the words and have the same meaning in language. But there are times that this is actually a big problem in terms of the actual content of what you're trying to describe. So I gave the example of 2 movie reviews where you could kind of pick out whether they were positive or negative by just looking at sort of key words in the reviews themselves. But there's also plenty of cases you can maybe, these are contrived, but it seems plausible as well, where the idea of, if someone says boring movie and not great, then this is very different from saying great movie and not boring. Those are kind of weird phrases to say, but to emphasize that it's not boring, I guess. But those are obviously very different sentiments there, and they are, of course, have the exact same words in them. So they would have the same bag of words representation, so we could not distinguish between those two in a classifier that just used bag of words, say. So this is kind of a problem. And so to move beyond this, I want to talk at least very briefly, and it's a little bit less clear maybe how we're going to use these things, because they don't result in like a matrix the same way TF-IDF scores do. But if you do the 688 problem, you'll actually use some of these language models to help you classify a document. So they can be used that way. We're just not going to talk about it too much. But the idea is we want to build some model of language that actually captures not just the words that are there, but also the actual order of these words, right? Because somehow it seems like order should be important when we talk about natural language. And in particular, we're going to talk about probabilistic language models. So you can certainly, and really every language model that describes real natural text really almost needs to be probabilistic. We don't think of language as being kind of a deterministic process where, given the past words in a document, you can know which words can come next. That would be kind of very boring then. You could generate all the documents you ever need to generate just by following this process. So there's some notion in which we believe language to be a probabilistic quantity. Now, we haven't actually covered probability yet, so I'm going to be a little bit, this might be a little bit forward-looking in a sense. But I think most people are at least familiar with the basic concept of probability. We were already talking about probability when it came to like the PageRank in a much more complex sense than this too, but the PageRank algorithm. So I'm just going to kind of use these terms without formally defining them, and hopefully it'll make sense on an intuitive level, even if the details maybe we'll wait till later in the course. So a language model, a probabilistic language model in particular, just tries to provide some distribution over words for a document, right? And again, you can actually kind of write this a little bit more formally, but I'll just sort of say for now that what it's trying to do is it's trying to provide a probability of word I given all the words that came before it. One, I'll use this to write a little bit less on the board. I'll use that notation there. But we're trying to determine what's the probability of word I. In other words, what values could word I take on given everything that happened before it, right? And so this is kind of an intuitive notion because we can kind of think of, it makes sense for to think about the previous context in a document kind of implying some distribution over what we're likely to see next, right? So if we take the first sentence from the class website, which says data science is the study and practice of how we can extract insight and knowledge from large amounts of something, then probably the next word being data would have a higher probability of the next word being hot dogs, even though actually grammatically they're both perfectly fine. And it's probably, there's probably both higher probability than some word like large amounts of quickly, right? Not even a noun, right? That would make even less sense. So we think of language as being something where the previous words in a document imply what the next word is likely to be. And in fact, as we'll talk about in a second, this actually also is, if we specify this for every single I, that actually also is equivalent to specifying a joint distribution over all the words. But again, I'm not going to talk about that because we haven't actually covered definitions of probability yet. But just If that makes sense, then good. If it doesn't, don't worry. But this is the basic idea, is that a language model in general would provide, and actually this is I'm not being at all restrictive here. I'm just saying that in general, language model will provide some distribution over the next word given everything that happened before, which is very broad, right? Because everything that happened before in the document can be really, really big. So how do you possibly sort of achieve a language model that really can capture probabilities given all the context we've seen so far from now? And there actually are reasonable ways to do this that are coming to the forefront right now, where you actually do use the entire past content to figure out what's going on and what your next probability is. But we're not going to do that. We're going to take a simpler approach here. I should also add that the true, I mean, it is possible to think of the English language as actually having a true language model. So in English, there actually is some notion of how likely one word is after everything that came before. And this encodes really everything in the entire world, right? Because it encodes all our common sense knowledge. It encodes, all facts about the world that somehow, if I say the sky is blue, that's somehow a more likely sentence than saying the sky is purple, right? Because the sky is blue. We believe that to be the case, most people know that to be the case, and so that sentence is more likely. That word has higher probability than previous ones. So in some sense, you can think of these things as encoding. Really, there can be some hypothetical encoding of all knowledge in a language model, but we aren't going to do that. We're not going to try to do that at all. We're not even going to try to think about all the context we've seen so far. All we're going to consider, in this class at least, is something very, very simple called an n-gram model. And an n-gram model says that the probability of word I is not going to be dependent on all the words that came before it, but just the last n-1 words. So if you've heard of these terms, this is also sometimes called a Markov assumption, or really in this case, a n-1 degree Markov assumption, but don't worry too much about that. All that means here is that this word depends only on words, I guess it would be I minus n plus 1. Is that what I'm doing properly? Yeah, up until word I minus 1. So that gives us n-1 words of context, and then we have from those n-1 words of context, we're going to ignore everything that happened before that and just use that context to predict the next word. So given this, this also seems that this also does put kind of a hard limit on the context we can actually use in a sentence. So in our example, this actually seems somewhat limiting, right? Because if you just look at, say, if you use n equals 4 n-gram, then every word, the probability has to depend only on the past 3 words. And so whether or not you pick data or hot dogs here depends only on the words large amounts of, right? So this is our oral sentence here where data science is the study of this. To determine what comes next, under the n-gram model, we only look at the previous, in this case, 3 words, right? And you can imagine that, if you only look at that context, those 2 possibilities are much more likely to happen, right? It probably depends on what you're talking about. Maybe not on a data science course webpage, but there could be other contexts where you're probably talking about hot dogs, like a hot dog eating contest or one of those things, right? You're probably more likely to say hot dogs than large amounts of data. They're probably generally now large amounts of data is a more common term than large amounts of hot dogs, so you can probably make a safe bet there as well in the English language. So the idea here, right, hopefully makes sense, is that we're throwing out all our context. And now, in addition to this, I'm also going to tell you one way where we can actually estimate these probabilities as well. And I want to emphasize that this is not the only way to estimate these probabilities. So if I want to estimate the probability of seeing large amounts of hot dogs, given that I've seen large amounts of, this is one way that I can estimate those probabilities. It is not the only way, right? Because this, for example, is not taking into account any external knowledge of the world. It just takes into account what we've seen in some corpus so far. So the idea here is that we're going to use a corpus, a set of documents, to estimate the probabilities in our language model. Okay? And we're going to do that just by counting. All right? So this is sort of the obvious thing. In fact, it's so obvious that this is what I want to emphasize, is that people assume it's the only way you can do this. It's not the only way you can do it. You can do other things, but this is a reasonable way if you only have this document at your disposal and you have no other additional information you can leverage to build your probabilities. Right? So what this says is, as you kind of may expect, and this is very kind of the natural thing everyone would do, the probability of this thing is going to be the number of times I have seen the words, I've seen this set of words to, in this case, all to I. The number of times I've seen all my words, including this word here, divided by the number of times I have seen the first n minus one of them. Right, so if I want to estimate the probability that the next word is data, given the previous three words being large amounts of, I would look in my corpus, look in my document, set of documents, and I would look at all the number of times that the phrase large amounts of data occurs, and I would just divide by the number of times the phrase large amounts of occurs, right? So presumably, if it's not the end of the document, there will be some word that happens after large amounts of. Actually, handling end of documents is a little bit tricky. Not that it's tricky, you can typically just ignore it, but it does cause some edge cases there. But presumably, every time the phrase large amounts of occurs, some word follows it. Right? And so to see if that word's going to be data or not, you just count the number of times that phrase occurs, large amounts of, and then you count the number of times, take the number of times the phrase large amounts of data occurs, divided by large amounts of. So in a simple example, another example, what would be the probability of word I in a 2-gram model, given that word I minus 1 is equal to of? Anyone? So also, this is a little bit tricky because everything seems so simple here, but I actually intentionally made this a little bit odd. What does that mean, this quantity? Is it a number? Yeah. Yeah, so I mean that definitely. So the question is, well, yes. So that is right, but actually, maybe I was actually being very, I was being very imprecise of what I meant there. So here, word I is a sort of identifier for the ith word, right? So is this whole thing like a number? Would that be a number? Would that make sense? Or should it be something else? Yeah. Right. So I mean, the answer I was looking for was exactly that one, which I'll say in a second. I think I was very unclear in my question. But the idea is, when I write something like this, what I actually mean is I want essentially a lookup for every possible word. What's the probability of that word, given that the past one was word of, though, right? So it's only sort of like a 1D lookup. If I write something like this, I actually mean a kind of a 2-dimensional lookup, right? Because I specify for every possibility this could take on, what's every possibility this could take on. So depending on how many of those equal signs I have, I mean kind of different things. But let's sort of just, define what I mean here. Boy, that's like really sticky today. Oh, there's a eraser jammed in the side. That's why. I don't like to get that out. No, it's going to be stuck there forever. So what is that? What are those probabilities? The probability that word I, say, equals free, given word I minus 1 equals of. What is this equal to? That now is a number, because I've specified sort of the value of both those two components. What is it? Yeah. It's 1/2. Same thing, but this is equal to, which other one is this? It's also 1/2. And this thing for for everything else is equal to 0, right? Because every other word has 0 probability of occurring under the definition I provided before. And so what I guess the answer is sort of what I mean when I say this first term is just the set of all of those probabilities, right? And you can think of it like a dictionary. A dictionary is a great way to think of it. That's how you would probably implement it if you actually wanted to. But then importantly also, if I just say this, I actually mean like a 2-dimensional dictionary, because I have to have a key for every word that could have happened before and every word that could happen next, right? So honestly, this sort of terminology is actually the hardest part of probability. Whether you mean a single number or a set of numbers is the things people get tripped up most about when you talk about probability. And I'll try to cover that a little bit when I cover a lecture on probability, but this is just kind of a preview for that. Just be careful, because it's not always obvious from the notation if people are talking about a set of probabilities or a single probability. So you have to kind of infer that from the context. Now, you probably see one problem here is that these zeros here are kind of bad news, right? Because if I think about the probability of, if I ever try to evaluate, say, the probability of some new sentence that was not a part of my corpus originally, then I'm very likely to hit one of these zeros, right? Because I'm very likely, especially if I have a long history, a lot of context, I'm very likely to encounter some phrase I've never seen before, right? And so then, what do you do in that case? Well, you can do a lot of things, actually. This is actually why even n-gram models can get complicated. But a very simple thing, and it goes by a few names, but I've always called it Laplace smoothing, though I know it has other names as well, is that you take you basically find some small alpha, and let D be the total number of words in your dictionary. And I basically say that I could consider seeing everything sometimes. And actually, by the way, what you divide by, it's actually, depending on different formulations, you might not want to divide by D there. You might actually want to divide by something else. It's like how many times you've seen that thing total. But, or just say, that this one works as well as any other. But basically, I'm going to say that I'm going to sort of suppose with some probability I'm going to see any word, given what I've seen before, and I kind of normalize that by the number of total words in my dictionary, so these still kind of become probabilities. And you can normalize by different things, and by varying alpha, you actually can get different models too. But the basic idea is very simple. It's just that you have some small probability that I'm going to see something, that some new word will occur, even though I've never seen the past context before. It's also possible to have more fancier things like backoffs. Like if I have, say, an n-gram where n equals 4 model, that means I'll use a context of 3. But if I've never seen a particular 3-word phrase before, then I fall back to a 2-gram model, or a 3-gram model, then a 2-gram bigrams, and then finally just the raw counts. By the way, a 1-gram model under this definition is essentially the same as a bag of words model, right? Because a 1-gram model says that the probability of each word is independent of any context that happened before it, and so it's just going to be sort of equal to the raw counts of the words you've seen before. I should have mentioned that before. But essentially, you can always do these kind of fallbacks to pick more and more, less and less kind of context-dependent models, and hopefully then you'll find some case where you've, well, at least by the by the 1 gram part, unless you have a word you've never seen before, which case is covered by this too, so you can kind of cover all your bases that way. So that's the basic idea of these n-gram models. Now, of course, the big question is, how do we pick n? How do we choose what n should be, right? And this is really a kind of a question not just about the nature, well, it's a question about a lot of things actually, but it's largely a question about data. So we know that if we have a smaller n, then we'll have less context with which to predict what the next word's going to be, which in some sense is always bad, right? We would like to actually have kind of the ideal case, we use all the words beforehand in our document to predict what happens next. If we use a smaller n, we're just sort of getting a worse and worse approximation to that. And so, and in contrast then with higher n, we always have more context, right? So with higher n, we have more and more past context to make it stuff. It's like right at the level where I can pin it against my pants and rip my microphone off a lot. So why? So which should we choose? And the answer here really boils down to data. So in theory, if we had truly an infinite corpus which dictated all possible language, then we should use essentially an infinite n. N should actually expand. We should use n equal to however many words are already in our corpus, because we have all of the English language at our in our infinite corpus now, and so, or whatever other language too. And so we should always use as big an n as possible, because that will always give us the most amount of context. Of course, we don't have an infinite corpus, and so in reality, we have to kind of make a trade-off. If we have a very small set of data that we've built in our corpus, then the chance of seeing certain phrases, certain long context phrases, is very small. And so what this is going to do is essentially, after you've seen a certain number of phrases, you are essentially will only see one word following it ever, and you're kind of pinned into that one possible next word. So it's not going to be a very good distribution. As you have larger and larger n and a finite data size, your distribution here will sort of start peaking towards only things you have actually seen exactly as you've seen them before in your data set, in your corpus. Question? Yeah, so I'm going to try not to use the words like overfitting and stuff yet, because I'm going to talk about that a lot more when I talk about machine learning. But that's exactly the idea, yes, is that you end up overfitting your training set, and you cannot generalize now to new documents you haven't seen before. And you can imagine, right, if you don't do this, especially if you don't do the smoothing, then once you have like a 4-gram model, there's a very high chance they're going to encounter some set of 3 words you've never seen before, and then your probability of everything is 0, and so you sort of are out of luck, right? The ideal thing you want to do is actually sort of use something like a holdout cross-validation set, which well, again, we'll talk much more about in machine learning. The reality, though, is for most English language, you can never go above 3 for your n. You will almost always start overfitting if you pick more than 3, in the true kind of cross-validation, the true sort of held-out sense. So probably n equals 3 if you have a very big corpus. If you have a small corpus, probably n equals 2. Kind of the rule of thumb. N equals 1 is pretty bad, because that's just the bag of words model. We already talked about that. So if you want to build a language model, you might as well do something a little bit fancier. Probably n equals 2. Maybe n equals 3 if you have a big data set. Okay, so now's the fun part. Now we get to see what these look like. So here I coded this up. I coded up a simple language model, which will be actually your assignment for the 688 class if you want to do it, or if you want to just do it anyway. They're not that hard to write. So I coded up a language model, and I trained it on the complete works of Shakespeare that I think Eric actually uses also as an example of some processing for the Jupyter Notebook tutorial class. So I use the same file there. And what I'm doing now, and honestly, the fun thing about these models is that you can not only use them to model language you've seen, but you can also draw samples from them. So you can actually essentially say, okay, I'm going to pick some initial, say, a two character phrase. If I have a n equals 3 gram model, I'll pick some initial two word phrase, and then I'll look at my distribution of things that come after that, and I'll draw a random sample according to my probability distribution there. And then I'll look at the next, that one and the one that came before, and I'll draw a random sample from that one, and I'll repeat this process. You could also pick the most likely one if you wanted to pick the most likely thing Shakespeare could have said, but you can also just go ahead and randomly sample them. And what's really interesting is that very quickly you get things that they don't make any sense grammatically or sort of meaning, from a meaning standpoint, but they're actually proper English. They sound like proper English. So the first one doesn't really work. The first one is a bag of words approach. So is in as stands God's revenge. Actually, that isn't horrible, but France pitched good in fair host. And it just sort of gets a little bit muddled there, right? There's no real, because it's just randomly sampling from all the words that Shakespeare uses there. So not very interesting. At n equals 2 already, you have a little bit more meaning. That just basically predicts the next word given the one past word. And it looks a little bit better. But n equals 3 actually looks pretty good, right? Again, it doesn't mean anything, but believe they all confess that you withhold his levied host, having brought the fatal bowels of the Pope, and that this distempered messenger of heaven, since thou deniest the gentle Desdemona. Again, means nothing, but takes a little while to make sure, given how hard it is to read Shakespeare anyway, it takes a little thinking to realize it's just nonsense. It doesn't actually mean anything. And then finally, you need to go a little more extreme and use n equals 7 as your n-gram model. And this actually makes a lot of sense here. In fact, it looks a lot like Shakespeare because basically, actually, it is Shakespeare. A lot of these phrases are actually just out of Shakespeare. Because again, when you have an n-gram model like n equals 7, there aren't many. You're using a context of 6 n-grams to predict what the next thing is going to be, and basically not that much happens. There's most phrases of 6 words are unique, even in the whole collected works of Shakespeare. Not all of them, so this isn't quite exact, but most words are unique, and so there's only one choice for your next word. Assuming your smoothing is small enough, and usually you make the smoothing pretty small, so you're basically just going to always pick the next word that actually occurred in Shakespeare. So you're just going to end up transcribing some passage from Shakespeare. So it's not that interesting, but there's an interesting sort of trade-off, right? That this is definitely not from Shakespeare, right? But yet it sounds kind of interesting, and as you go between the two, you get something which is generating novel text that no one has ever thought of before. It sounds like Shakespeare, but which is utterly meaningless. So that's very fun. And again, extremely simple to write. This is about 15 lines of code or so to do this. Yeah. So for n equal to 1, because there's no context, there's no words that came before it, you just look at all the words in all of Shakespeare, and you sample them in proportion to how often they occur, right? So basically, your denominator becomes the number of times the previous thing was nothing, which is the number of words in the corpus, and so all your probabilities are just the number of times. All your probabilities are just the number of times a word occurs in the entire works of Shakespeare, and so you're just randomly sampling words in proportion to how often they occur in all of Shakespeare. The next one you sample, assuming you have the one word, given that one word, you sample the next one from this distribution, etc. Yeah. All right, so the last thing I'll say before I move on to some libraries to do this, though actually, unfortunately, there aren't that many libraries that do exactly this, sadly. There used to be, but they took out some of the code that does it. I'll get to that in a second. I'll kind of rant on that in a second. Anyway, so I think kind of a key question that we have, though, is how well do these actually perform? And so a standard way of evaluating how well a language model works is to evaluate something called the perplexity. And perplexity is just sort of a fancy word for a scaled version of the probability. So, an obvious sort of way of determining, how well is a language model fitting some text is to say, well, what's the probability of that text under the language model, right? That would be sort of very natural. And in fact, we can do this. Again, I'm being a little bit imprecise here because when I have an n-gram model, I'm just starting at the nth word so that I always have context. So I'm ignoring the probability of the first n minus 1 words. I just assume we're sort of given that at the beginning, and I'm only evaluating the subsequent ones. This is actually not quite correct. This is violating some laws of probability, but it's going to ignore that. So the probability of this should be big N here. That's actually quite important. This should be big N. This is the probability of all the words in the document. Big N is the number of words in the document. So maybe I'll just write this. I should probably also put this notation there. But big N equals number of words in the document. And little n equals the n from the n-gram. That n. This should be big N. But if we have a whole document that has n words in it, we can approximate the probability of that document by this is sort of according to our actual language model, as the product of the probability of the ith word given the words that came before that, where I ranges from, it really should range from 1 to n, but to keep things simple, I'm just going to make it range from our n-gram word to n. This basically just ignores the probability of the first n minus 1 terms in the document. All right, so I should probably put approximately equal to there, but it's close enough. So we can evaluate now the probability, given a document, we can evaluate the probability of that document under this language model. But that's sort of that's a tricky measure, mainly because they're all so small, these things. They're all tiny. Because every time you're multiplying by 0.5 again and again, every time the number of words are, these things quickly become extremely small, these probabilities, in an absolute sense, right? So basically the idea there is that because there are so many possible documents, the probability of any one document is very, very small, vanishingly small. So, and in fact, doesn't go to 0 as the number of words in the document become more and more. So to get around that, most measures of how good a language model fits a document actually, in some sense, normalize by the number of total words in that document. So perplexity is one very common measure, and you could actually write it 2 different ways. It's actually 1 over the probability to the root to the root n, so to the power of 1 over n, where n is the number of words in the document. And that just sort of normalizes in a nice way. It's oftentimes actually easier to both compute and write it like this, where it's 2 to the log 2 of the probability divided by n. And that's nice actually because when you take the log of that probability here, this product here becomes a sum. And so you can compute these things without, without overflowing your floating point operations on your computer. So those are the same. But this is just, all it is a normalized version of probability or really inverse probability. Here, lower is better. So a lower perplexity is better. The model fits better to the document. And it's just a normalized version of the inverse probability of that document. So what does perplexity look like then as we increase, say, the order n of our n-gram model? So if we just look at the corpus that we use to train or to build the model, then perplexity of that model evaluated on corpus will always decrease as we increase our complexity, right? And that makes sense because basically every time we add in more context, we know we're not going to find something we haven't seen before in our document. We're training it, we're building it on this document. But what we're doing in some sense, we're also kind of kicking out things that we know don't occur. So after a certain given a certain context, in our document, one thing happens next. And if we build a language model, well, that's the only possible next option. That'll have probability 1, and so it'll have very low perplexity. The probability is very high of this document. So as we increase our order here, the complexity lowers. In other words, the probability of the document increases. To the extreme case where if we could have a language model where both all phrases were unique and we sort of counted every infinite context, infinitely large document, then the complexity would be 1 as we increase the order. Sorry, complexity would be complexity would be 1. The probability would be 1 too. So that's sort of that's great, but it isn't really what we care about, right? Because we don't really care in some sense about. And this, by the way, this actually is on the Shakespeare text. This is about complexity over different sizes of n. But what we care about in some sense is not this. What we actually care about is what happens on some new piece of text, right? So I can actually also build my probability tables from the first, say, 3/4 of all the Shakespeare texts, and then evaluate how well it works on the last quarter of Shakespeare's text. And you see a very different story now. So now, actually, after n equals 2, from the perspective of actual perplexity, we are doing worse after n equals 2. So we go down a little bit from 1 gram, no context at all, to having 1 word of context. But even 2 words of context actually don't help us from a complexity standpoint. And the reason here is that with this sort of smoothing, whenever you find a phrase you've never seen before, you pay a high penalty, right? Because that's going to be this alpha over alpha d term, which is small compared to most anything else. Or rather, if you see a phrase where you have seen the context before, but never the next word in the new document, you pay a high penalty because essentially you have alpha over some big number, which is going to be a very small probability, and that's going to be really hurt your complexity score. So from a standpoint of actual evaluation here, actually, you quickly go up here. Maybe this is actually a suggestion that maybe this is not the best metric for perplexity, sort of raw perplexity here, because I thought that n equals 3 was probably better. I mean n equals 2, but it's not a perfect metric either. Okay, so I'm going to very briefly now mention some libraries to do some of these things. But are there any questions first? We'll actually finish this lecture in this course. So we're back on track. All we have to do is leave out an entire lecture. No problem. All right, so let's talk a little bit about a couple Python libraries. And I'm actually here I actually didn't put up a notebook to do these things because you'll do some in your homework, but actually I don't really like these libraries that much. I'm not that big a fan of them, so I don't necessarily want to use them for your homework. It's the ones people use, but I don't think they're actually that useful. So the library everyone uses in Python for natural language processing is called NLTK, which stands for Natural Language Toolkit. It's a Python library for doing a lot of different operations related to natural language processing. It's a little bit more geared towards more complex operations. So it's a little bit geared more towards tagging, which means finding the part of speech, the different words in a sentence, and also parsing, which means computing like a parse tree, a grammatical parse tree of sentences. Ironic to note that you cannot run an off-the-shelf parser using it. It's not including any off-the-shelf parsers when you download it, which is very annoying. So you have to find other parsers that you can import into it. But it does okay in those two. But it's really much more meant for those, so for a deeper level of natural language processing, processing than what we're talking about here. And so it's really only marginally useful for the stuff that you're going to be doing in this course. But it's still what everyone uses, so you should probably know about it, know some basic calls, and that's all I'm really going to highlight here. You may also want to look at other libraries too. There are other ones that I think are actually probably a little bit better. They just are a little bit more off the shelf. You can download them and just start parsing stuff right away. You don't have to mess with oddities of dependencies and stuff like that. So things like libraries like Spatie and Core NLP are two examples. If you want to do one of those for your tutorial, that would be a great topic. But I guess I've already committed to tutorial topics. You can still change if you want to. Okay, so let's look at a few things. So let's look first. You can import the library with import calls. Also, I think we're going to use the .corpus submodule to do stop words, find stop words. And the first time you run it, you have to run this nltk.download function. This is actually part of the reason why I don't like this library. Is that you have to download its own package manager that manages its own packages for NLTK. It's very odd. But I mean, there's a lot of good content there too, so I shouldn't be too discouraging. There's got a ton of work put into this. It's just kind of an odd way to package a library. So run that once, uncomment that, run it once, download a bunch of stuff. Don't download everything, because some of the things are actual libraries of corpuses that are like multiple gigabytes to try to download. So don't do that. Just pick a couple of them. You can do these things. You need one to do the parse speech tagging. I forget which one you need, but you need one of them. And then you can do things like now tokenize words. Now, this is a lot of effort to basically do a split call, right? When you bounce to a split call, you're taking a sentence like this and you're tokenizing it. The one thing it'll do though, or a couple things it'll do, is it'll actually take some phrases like conjunctions, so isn't, I put in there intentionally. It'll break it up into is and int, which is not, to sort of actually help process some of these things. One thing that it can do out of the box, which is quite nice, is part of speech tagging. Though it's not necessarily the highest quality tagging for as far as NLP, advanced natural language processing goes. There are better taggers out there, but it's pretty reasonable for something that's downloaded off the shelf. And what that does, that actually takes this sentence and attaches parts of speech to every word there. So it'll tell you if it's a noun or a verb or an adjective, etc. And it's actually smart. It's not just looking things up. It's actually using their context to tell you. So for example, here text processing. So processing here is actually a noun because text processing is a phrase, so that actually is considered a noun. But it can also be a verb, right? In a different context, processing could be a verb. And if you tag it, it'll correctly say that you're processing is a noun. N-Ns are nouns, JJs are adjectives, VBs are verbs. I forget what the rest stand for. There's special cases that I'm not a linguist, so I always forget what they mean. But it does a reasonable job of that. So that's sort of nice. If you want to go beyond even sort of the simple words, you might want to use, in like an n-gram model even, you might want to use not only the word itself, but also the word and its part of speech, because what happens after the word processing probably depends on whether processing is being used as a verb or a noun. So. A couple of things you can do with NLTK. You can get common stop words. So you can call NLTK corpus.stopwords.words in English and in other languages as well. You can get kind of common words for those. So you can also do things like list out now my sentence. So my sentence was, the goal of this lecture isn't to explain complex free text processing. And if I remove the stop words, then I remove things like, I guess I remove be and of and is and this. The things you would think to remove because they're pretty common, so they're probably not very likely to actually contribute much to, say, a classification. But by the way, if you're building an n-gram model, don't remove stop words because they do matter for the actual grammatical structure of a sentence. They just probably don't matter as much for the TF-IDF scores. And you can there also is one kind of handy function to generate n-grams, but you can actually do the exact same thing with just a longer, slightly longer, but a little more opaque single line of Python code. So in the 688 assignment, you're required to generate n-grams because you're going to build an n-grams model. You can't use NLTK because then you could do other things that would kind of be cheating. So you have to do it with sort of raw Python. And it turns out you can actually do the exact same thing with one line of Python. So if you're in the 688, you can use that. I won't make you figure out how to do that. Okay, so the last thing I'll say is actually, ironically, NLTK. What time do I have? I have 4 minutes. NLTK actually, I was excited to use it because I had in the past used it to have an n-gram language model. And I found out when I was looking for this lecture, they actually removed the n-gram language model because it had lots of bugs in it. So it was really buggy, and so they removed it. And so with your version that's in your version of Anaconda right now, there is no more n-gram model. They just took it out entirely, which is kind of a bummer. So you can't do this. if you check out a different branch from the GitHub repository that's under development, there is a replaced version that is completely undocumented anywhere and which has a frankly bizarre syntax that's trying to be general, but I think this makes it harder. So anyway, they're trying to replace it, but it's really... It's undocumented. It's just going into like a development branch. So I'm not even going to try to describe how to do that. So unfortunately, what this means is there's no longer any way to build n-gram models, which is like the first thing you do in any NLP, or one of the first things you do in any NLP course. Okay, so anyway, I'm also done ranting about that. The second thing is there's also actually no way to create TF-IDF scores in NLTK, which is not really its fault. It's not really that's sort of a very that's much more of kind of a like information retrieval type task or machine learning type task, and so they just don't have that kind of stuff there. So in fact, if you do want to create TF-IDF scores, the library to use, or even frequency count scores, the library to use is actually scikit-learn, which has a very nice interface for creating these things. Scikit-learn, we're going to talk about a lot more coming forward, because it's a very sort of standard and nice machine learning library for Python. Some people I know have already used it a little bit to like normalize columns or something like this in a matrix. But it's a very nice library, not always the fastest implementation, but a very nice one. And it turns out it has a very nice way of creating TF-IDF scores, or at least they're actually a different definition of TF-IDF scores than what we use, but it's good enough. So this is kind of an odd place to introduce scikit-learn because we're going to talk about it much more, as I said, and we're going to talk about it in the context of the machine learning algorithms it does. But it does have this sort of nice way of generating both frequency counts and TF-IDF scores. So you actually, I think you may be able to do this on your homework. You may have to do it in NLTK. I forget which exactly, if we're going to force you to use NLTK or not. But there's a class called the count vectorizer, which essentially transforms data like this, where you have an array of strings separated by spaces. It will, in one line of code, convert that to a counts matrix. So that is that first step that I showed a while back of just creating the X matrix of frequency counts. So you can take the counts vectorizer. You can actually even put stop words directly in there, and then just call a function called fit transform for your data, and that'll return a frequency matrix, in this case as a sparse matrix. So it's nice because it actually is returning sparse matrix without going through so it will not create too big of a representation. It will use a sparse matrix format to do that nicely, even if you have a very large set of documents or a very large number of words. You can also create a TF-IDF matrix using a class called TF-IDF transformer, and this function fit transform. So this is a sort of weird convention here, but this is how scikit-learn works. You create objects and then call either a fit or a fit transform function to actually apply that method to some data. That is the way that these things will work. You'll see a lot in machine learning. But you can, for now, just kind of use this as a black box to generate both frequency count matrices and TF-IDF scores. One caveat, though, is actually, I don't know why, but they decided to use, instead of normal TF-IDF, they decided to use TF times 1 plus IDF, which I guess means that even if IDF is 0, you will still have some value for terms in a document. So like if every document had the word of, it wouldn't actually get rid of it here. So just be aware of that. This is actually not the same as IDF that you can see in class. And so for example, in your homework, I think actually only in 688 are we asking you to do that, but in 688 you have to rate TF-IDF. You actually couldn't use scikit-learn anyway. That library is not allowed in that portion, but it wouldn't work even if you try to use it because it's a different definition. All right, so this actually concludes our unit on data processing. As I said, we missed out on geographic data, but I will write a tutorial on that you should read both to learn about it and as a guideline for the kind of things we may want in a tutorial. But next up, we are now moving to the world of statistics and machine learning. So that will be the start of next lecture.
Let's see.